Okay, so last time we talked about the when small r is equal to capital R over 3. So here, before we try to plug in small r to be capital R over 3, we try to find a closed form solution when r is smaller than capital R, and of course larger than 0. So we try to find a closed form solution for the E field in this range. So here, the Q enclosed by the Gaussian surface. Okay, so suppose this is a Gaussian surface, and actually we have the radius to be capital R. This is the radius of the sphere, and within it there are some charge density which is proportional to the radius. So which means that at the center, okay, the density is smaller, and close to the radius, the density is maximized. Okay, so here, when we consider Gaussian surface to be this small one, so we only integrate from 0 to small r rather than capital R. Okay, so and here is actually the same as part A. So we do the integration. So here we have a rho s over capital R rather than small r, and then we have a r to the fourth power over 4, and then we still have 2 for this integral, and then 2 pi for this integral. So we have this 4 and this 2's can be cancelled, and then the answer should be pi rho s times r to the fourth power over capital R. This is the enclosed charge within this region. Okay, so we consider this is the Q enclosed by the Gaussian surface. Okay, so here when we try to apply the Gauss law, so this is the Gauss law. Okay, on the left side, actually the epsilon naught times the total flux. The total flux, when we assume all the things are uniform and parallel to the area vector, then we will have, this is the surface area 4 pi r squared, and then times E will be the total flux. And then, yeah, so the left side look like this, and then the right side will be Q enclosed. And then we try to substitute. This is the Q enclosed to here. So on the left side is the same, and the right side we have pi rho s times r to the fourth power over capital R. Then we can have some cancellation. So this pi can be cancelled with this pi, and r squared and r to the fourth can cancel down to the r squared. Okay, so finally we move this epsilon naught and then also 4 over. So we have 4 epsilon naught capital R in the denominator. And then in the numerator, we have rho s r squared. So rho s r squared here. So this is the closed form solution when we consider R is smaller than capital R, which is required by part E. But of course, in part C, what we need to find is the E field magnitude when R is equal to capital R over 3. So we can just plug in. We can just plug in E to be R equals to capital R over 3. And then, which means that we have rho S and then R squared. So we have a capital R over 3 squared all over 4 epsilon naught times capital R. So we just substitute R capital R over 3 to here. Okay, so in this case, we have 3 times 3 is 9, times 4 is 36, and then times epsilon naught. And then this R will cancel with one of the capital R here. So we have rho S capital R on the top. Okay, so here we can just substitute the number. Rho S is this one, 35.4. Pico is 10 to the minus 12. I asked you to remember the scientific prefix before. And then R is 5.6 centimeter. Change it to SI unit, which is 0.056 meter. And then over 36 times epsilon naught is 8.85 times 10 to minus 12. Okay, so the answer will be 6.22 times 10 to minus third power. And then the unit is, of course, a Newton per Coulomb. Okay, so this is the answer for part C. Okay, so the next part is when R is equal to capital R. So nothing special. Actually, we can just substitute R equals to capital R to here. So we can quickly come up with E R equals to capital R. Actually, you may have concern is that we only write smaller here, but actually smaller or equal to will be the same. But if R is larger than capital R, it might be different. But yeah, but actually we might need to also find when R is larger than capital R. So let's try also to come up with the closed form solution when R is larger than or equal to R. So we can be more familiar with the Gauss, how to apply the Gauss law. So actually, we already know that the total charge is Q. So this is the radius R, and the total charge Q, we have obtained it in part A. So there's no problem. The Q enclosed will be nothing but the total capital Q. And then here we would like to have this Gaussian surface with the radius small r. So in this case, when we try to apply the Gauss law, so epsilon naught times integration of E dot dA equals the Q enclosed will be the total Q. Okay, so here we have a epsilon naught times E times 4 pi r squared, which is nothing special, the E times the surface area. And then Q is this one, pi rho s r cube. Pi rho s r cube. So we can come up with the expression as E equals. So we have here 4 pi epsilon naught to be here 1 over 4 pi epsilon naught. And then we have this, let me see. Okay, maybe we can do some cancellation first. So we can actually cancel this pi and this pi. Okay, so we have a 4 epsilon naught at the in the denominator, and then we also have this r square. So we have r square here, and then we have rho s r cube as this one. So this expression is for r is larger than or equal to capital R. And actually, you can feel free to plug in R equal to capital R here for finding E at R equals to capital R, or maybe you can just plug in R equals to capital R here. The answer will actually be the same. So here we just choose one to do this part. So E of R equal to capital R will be rho s r cube over 4 epsilon naught capital R square. So we just plug in this R to here. Okay, so here we have rho s R over 4 epsilon naught. Okay, so then we can plug in the values. Rho s is the 35.4 times 10 to minus 12, and then times capital R is 0.056 meter, and then over 4 times 8.85 times 10 to negative 12. So the answer will be 5.60 times 10 to minus 2 Newton per Coulomb. Okay, so this is the answer for part D. Part D. Okay, so and then for part E, we would like to graph E versus R. So let's reiterate the expression of E will be rho S times R squared over 4 epsilon naught over capital R. Okay, like this. So this is R is smaller than or equal to capital R is larger than or equal to 0. Okay, like this. And then when R is larger than or equal to capital R, it will be rho S times capital R cubed over 4 epsilon naught R squared, like this. Okay, so when we try to graph it out, we can have a simple observation first. So except small r, all the other terms are constant. So when r is smaller than capital R, it is proportional to R squared, proportional to R squared. And when R is larger than capital R, it is inversely proportional to R squared. So when we try to graph it out, it will be like this is capital R, and then this is the R axis. This is the magnitude of E, and then in the y at capital R, this point will be the maximum E field, and then when it is smaller than capital R, it increase as a square function. However, when it is larger than capital R, it is decreasing, with a inverse square function. So this part is proportional to R squared. This part is proportional to 1 over R squared. And this point is nothing but 5.60 times 10 to minus 2 Newton per Coulomb. Okay, so any question? If you have a question, you can raise it in the chat room. Otherwise, we will end this chapter here. So this is September 5th.